Okay. Hello, everyone. So welcome to our third round of CISPA European AI and Cybersecurity Hackathon Championship. So thank you all for coming here. We know it's weekend, Saturday, and you are here with us to work on these challenging tasks about AI and cybersecurity. So we are really proud of you that all of you came here and you want to compete in our championship.
And there's one organizational thing. We see quite a lot of people here, yet so far we have only 56 people who registered outside with our team. So if any of you has not talked to our team and got a check mark next to their name and got the info material and all of that, then please do so after the opening ceremony. So we just need everybody who is here to be registered outside.
Well, actually, it's a very special competition today. So what we would like to announce is that actually this is Valentine edition of our CISPA European Championship. So we know it's not only Saturday in the morning, but also Valentine Day. So now we know all of you love AI and cybersecurity. That's really amazing. That's really great. Okay, so first of all, probably, we talked to some of you already, we got to know you, and then there were these questions like, who are you guys, So we thought okay, maybe first we'll just give a small intro to who we are, where we come from, what we are doing. So I can start from myself, because I'm already speaking. So my name is Adam Dziedzic, and then how I describe myself is that I am a researcher who travels the world to work on different aspects of AI and security. So currently, actually we are both faculty members at CISPA in Germany. And before coming to Germany to work on AI at CISPA, actually we were both postdoctoral researchers, so we are so-called postdocs, in Canada at the Vector Institute and also University of Toronto. And actually these are amazing places. They are also these birthplaces of modern AI. So this is an amazing environment to also work on AI. And before joining Toronto and Vector, also in my case actually, my PhD in the US, University of Chicago. And also I also work in many different companies, organizations. So for example, I did work at Google, Microsoft Research, Barclays Investment Bank. Also I work at CERN in Geneva, and literally you name it. And then currently, I'm really excited because we can come here, we can go across Europe, and we can also share our knowledge and also passion for these aspects of AI and security.
And my name is Franziska. As Adam already said, we are currently faculty at CISPA, and before I was also in Toronto at the Vector Institute for AI. And I personally come from more of a security background, so I got my PhD in a security institute in Germany. And I also had various research stays over Asia and Europe, and got to know different ways of working, but I've always been super excited about this intersection of AI and cybersecurity.
Okay.
And as of for today, we're not alone here.
No. So who is there with us? So we can introduce also our team. So we have a technical CISPA team here at the hackathon. Also we have with us Torsten. So Torsten can also wave. Also he will describe his one of the tasks. So actually Torsten also was intern at Vector in Toronto. Also he was a postdoc at TU Berlin, and now he's also faculty member at CISPA. We also have Venhao Wang, who is also our PhD. Also Venhao, if he is here, can wave. I think it's over there. Also we have Antoni and Aditya over here. We also have Ivo is here, and Maitri, and Nima, and Jonathan over there next to Torsten. This is our technical team. If you have any questions, especially regarding we will show you basically our leaderboard, any task, then there are actually people to go and consult, to ask questions. They also are experts in this area, so you can even learn from them a lot of things. So please, by all means, approach them, ask them questions, also us. So we are here to just also help you to learn about these exciting topics. So apart from our technical team, also we have other team members from CISPA.
And we have from the general organization, we have Julian, who's basically in charge of many of the things here. And with him we have Sabrina Ute, and from the talent acquisition team today we have Flavia, Kira and Pauline joining us. So if you afterwards are interested in like finding out more about CISPA and who we are, those are the people to talk to about career opportunities like PhDs and research stays at CISPA. And finally we have Tobias, who is our person for everything that is related with public relations. So you'll be finding him, like, go around here, take photos, and he'll be very happy to talk to you. And now to give you some background of where we all come from, CISPA is located in Germany, more precisely at the border of between Germany, France and like Luxembourg. So in Saarbrücken we do have this amazing center which focuses on different aspects of security and machine learning. And we are a very international community with more than 700 employees from over 66 different nations. Our working language is English, and we learn and study different topics of security and machine learning in currently more than 40 different groups of faculty who each have their own research focus. And there's one thing that joins us all at CISPA, which is our scientific excellence. So if you look at the CS ranking, which is the current ranking where we rank institutions according to what they achieve in terms of academic output, if you look at the area of cybersecurity, CISPA is #1 in the entire world. So this is before like many of the elite universities in the US and over Europe. But I think this speaks for itself that at CISPA we do outstanding research. And for example, at Adam and me, we're co-leading the group which is focused mostly on trustworthy machine learning. It's called the SprintML-Lab. And just with us, we currently have around 20 members, including postdocs, PhD students, interns, and student researchers from various nations. And if you want to find out more about what the team particularly does, you can also visit us under sprintml.com for research collaborations and opportunities. And today we're excited to run the third local hub of the CISPA EU AI and Cybersecurity Championship. And this means like we had already 2 very successful rounds. The first round we had was in Paris last November, and the second round in Vienna. And now here's the third hub. There are 3 more to come. And what is great about it is that the 3 top teams from all of the European hubs will meet eventually at CISPA in Saarbrücken to compete in the grand final. And if you made it to the final, then you're already qualifying as a runner-up. So if you're in the top 3 today, you're a runner-up already. So congrats in that case. Then like you see that you will be already getting an award for your team. But if you manage to even beat the other winners in the final, there's more award to get, and the first place to compete in the final will get a 4,000 euro prize, the second a 2,000, and the third one a 1,200 euro prize. And of course, for all the teams that win in the local hubs, the travel to CISPA will be provided. So you also already, if you win here today in the top 3, then you already got yourself a trip to Germany. And to talk about what will happen today, is that we are now already in the opening session, and after the opening session the hackathon will begin, because today we had a lot of like teams that were still to be formed and people that will still to be merged. We will need another few minutes after the opening ceremony to actually send out the emails to all the teams, because every team will get an API token and will get their unique identification here. But because the teams were like still a bit unstable by this morning, this will take us a few minutes, but like a bit after 2:30, after midday 30, so 12:30, we'll be beginning with the hackathon, and then it's hacking time basically, so you can get started on the task. At 5, the dinner will be delivered, and then you can basically hack the whole night, solve all the tasks, and tomorrow morning there will be breakfast, and at 12:30 the hackathon will end, and there will be lunch delivered. And we will have the top 6 teams present their solutions in the presentation. So basically, we want to learn, of course, how the best solutions perform and what is behind that. So we will be asking people to just, like, if you're in the top 6, present like short presentation and then talk about what you achieved. And finally, based on the presentations that we saw and based on the scoreboard, we will be awarding the top 3 prizes. in a results ceremony at 3 p.m. And finally, if you haven't done so yet, we do have a Discord channel. And this Discord channel will be your go-to for the next 24 hours. We'll be having all the information, like what is happening in the task. If you have technical challenges, you can reach out there. So please join this Discord if you haven't done so.
Please scan the code for those of you who haven't joined yet, so that you can also learn about not only tasks, but also, for example, where is food, when is food, and so on and so forth. So this is really your way to go and find information about this hackathon.
All right, and then during the whole hackathon, we'll be having a leaderboard. This leaderboard is about showing you what is happening. So we'll be solving 3 tasks that we teach you about. And basically in these tasks, every team will then be ranked. And the ranking is done in such a way that we have like some split of the data. So we do have a held out set, which is for those of you who are in machine learning already a very common phenomenon. So we have a set of data that we evaluate your solution on, and it will not be the same data during the hackathon as like after the hackathon. So we have a split of like 70% of the data which are for your final score, and then 30% of the score that you will be shown during the hackathon. And you will always see on the scoreboard your best solution. So even if at some point you do something terribly wrong, your best solution will always be stored and basically show you the score. And there's one particularity today, because the third task that you're going to hear about more later is a white box task, so you get access to everything, evaluation score during the hackathon, and at the end will be the same.
Mm-hmm. So maybe also one thing about the scoreboard and how to work on the tasks. So as we talked to some of you, and how it really works is that we recommend the teams to be of size 4 people, 3 people. I think ideally it's 4 people, and then we are here to also help you learn about these tasks. And what is important is that, so you should work on all the tasks. So ultimately, we aggregate the results from task 1 to 3 into this overall ranking. So if you want to win, if you want to advance to the final, then actually the whole team is supposed to work on all the tasks. So that means it's very important that probably if you are 4 people, you can just try to maybe divide a bit who works on which task. You can also collaborate, of course. I think this is highly recommended. However, at the end, the overall ranking is based on all the 3 tasks.
And the presentation, yeah.
And also the presentation, right.
Are there currently people who are still looking for a team? Would you maybe raise your hand? Okay, that's great. So
Okay.
like all of you seem like, I think you saw who raised their hand, so probably it would be good if you could just reach out to each other and merge.
Yeah, for example, you can. So what I would recommend is that after this info session, if those of you who are still searching for a team, please go to this corner, okay? And then we also help you. I think Aditya probably also can moderate, and we can help you to form teams. I think we have 6 people who are still trying to find a team members. So we'll try to help you, and please come here and we'll form the teams for you.
And exactly, then you can let us know for the registration what is your new team name potentially, and then you're good to go.
Also, I think that we should mention that kudos to Nima for organizing this nice scoreboard. Also to Aditya for forming all these nice like teams and displaying that. So this is really like a great effort from our team to prepare this cool scoreboard. So yeah, probably also like a few maybe things about organization. So we should mention that. So if some of you don't want to be in the photo, so actually we have Tobias who takes photos. You can of course get famous thanks to that. We put the photos on LinkedIn or other social media. So, but if some of you don't want to be in these photos, please contact Julian, who is there, and he can actually give you this red badge. So then we know that we should not take photos of you, okay? Second aspect is that, so here we are guests at KTH, so we are really thankful that you can be here and we can organize this great event in this place. So please don't smoke on premise. If you have to smoke, then please go outside. So this is one of the requirements. And also, please keep the rooms tidy, especially once you are done with the tasks, you want to leave. Please also clean up after yourself. And this actually is just to help us organize everything and for everyone to just have fun and no problems.
Exactly. So for example, like if at the end the pizza comes and you grab a pizza box and bring it to your room, please bring it back when it's empty. All right, then I think we can go into the first task. So now it's about what you will be working on for the next 24 hours. And the first task is provided here by Ivo, and it's a really cool thing. So like to give a bit of context, so we train on a lot of data today when we train machine learning models. That could be, for example, photos of your friends or of your pets. And when you train a model, then basically the model gives some labels to all the data points, and then you'll see that the model is at the beginning probably pretty wrong. So you need to update the model with a loss function to predict the correct labels. And in this process, which is then the learning through backpropagation, you fit the model on your data, so the model learns from your data. But what happens by that is that information from the data slips into the model. So like the model contains this information in some various forms. And now, of course, this can turn into privacy risks because people have shown in research that the data can be eventually extracted. And there are multiple places where privacy could leak. If you already have access to the training itself, then you could already see that in the model updates. So if you have access to the final model eventually, then you could, for example, extract this knowledge from the parameters. Or, and this is the setup that we're going to look in today, even if you only get access to the model predictions, you can find out about the training data. And that, of course, is a problem if that data is private. So there is an attack that is called model inversion. And let's say you train your model on this standard MNIST dataset here. And MNIST consists of these like numbers from 0 to 9. So you train the model, and then you do the model inversion. What it gives you at the end is some form of prototype for every class that you trained on. And now you might be thinking, okay, a prototype of this class, like how private can that be? But now think about other models that are trained, for example, on faces. So to classify faces, you log into your phone with your face and it recognizes you versus others. So a prototype of your class is eventually like a prototype of your face. So this will be extremely privacy disclosing. And how the most naive form of this attack works is that you just need some noise as input to the model, and then you say, I want to reconstruct class 5. So what you do is you look at the model output, how confident is the model about the class 5 output, and let's say the model is not super confident, right? This looks like noise, so why would it be a 5? But then what you can do is to backprop, so to basically do this learning procedure, but this time you keep your model stable, but you keep your initial noise learnable. So you get information on what would you have to change in this noise to be more likely like a 5. So, and this is differentiable, so you can learn it really. And you do that over a few iterations, always saying, okay, I want to increase the confidence for class 5. And over multiple rounds, then your final input will look more and more like a 5. And you will have extracted this prototype. And today we're going to be in such a setup where our team has generated for us with the model Infinity 2B some training data. We have generated 5,000 training images and 1,000 auxiliary images. And we took the original 5,000 training images to train the model classifier for you. And we will expose this classifier for you over an API where you can send images and then get the logits for it, so the model output. And your task is to extract or reconstruct training data. And because it's super challenging to extract like all the data, what we ask for you is to submit us 100 reconstructed images of which you are most certain that they resemble the training data. And then we'll be comparing the images that you sent to us with the original training data. Like there will be a one-to-one mapping for each of your image that you send. We'll be greedily taking the closest image from the training data. And then for the second one, from the remaining 4,999 images, we will take the closest one. And we will be calculating the mean squared error over these data points. And then we'll give you the score basically as the average mean squared error on these 100 reconstructed images. Are there any questions about this task so far? Please.
Can you explain the auxiliary dataset?
Yes, the auxiliary dataset is just data that has been generated exactly the same way from the model. And this is just for you because you will never know how the training data looks like. but this auxiliary data is from the same distribution as the training data. So it will just give you an idea how this data should look like, and potentially you can start optimizing from there instead of random noise. Sure.
Any more questions?
Please go ahead.
Any limitations on the API?
Yeah, that's a good question. So we do have limitations on the API, which is that you're not allowed to basically brute force the API, because this would cause like eventually the server to be flooded. It would be like a DDoS attack, and it would basically make the hackathon not fun for everyone. So we do have cooldown times. So every time you submit a solution, there's a 5-minute cooldown if it was a successful submission. So you cannot just like brute force your way through everything, but like only submit reasonable solutions. And then if you have a missed solution, like let's say you submit as 99 images instead of 100, so the shape is kind of mismatched or something is wrong, then you will have a 2-minute cooldown until you can try again. So really try to make kind of reasonable solutions such that you get a regular signal on what is good.
Do we have a list of images that we have to impute in there, or we just pick up an image for ourselves?
You can input basically anything which is correctly formatted. And the correct formatting is here 32 by 32 by 3. So like if you want to, you can start by inputting random noise potentially.
How many images can we input at the same time?
At the same time, 100 always, yeah. Okay, any more questions? Otherwise we can move on to the next task.
Okay, so no more questions for now. So we can move to the second task. Actually, second task is model tracer. So this is kudos to Biche and also Maitri, who work on this task, so that you can work on that today. So what is really motivation for model tracer? So nowadays, generative AI generates these futuristic videos. Also, thanks to these models, we can also produce photorealistic images and as well high quality music and text. But with this great power of this generation of high quality content also comes great responsibility. So what are really the challenges to ensure that we have secure generative AI? The first aspect is misinformation. So we want to make sure that actually this data generated actually does not cause misinformation, that we don't read fake news, so high quality content of text and images, but they might be just not real. Second aspect is that we also want to make sure that actually we generate this data safely, meaning that we don't generate harmful content that can also, for example, cause some problems down the road. Then also we want to verify what are the sources of the data that actually is used to train the models. So we want to find out what were, for example, the forms of text or images that were used to train models from, for example, OpenAI, Google, or Anthropic. And finally, also we care about where the information, where this content comes from. We call it provenance. So we want to really trace the origin of the given content, of the given image, of the given text. So it can be, for example, that this image might be just painted by a human being, by an artist, or can be generated. So this actually last aspect is the theme of the task 2, model tracer. So in model tracer, we want to attribute an image to its source. So we are given, and you are given, in this case, an unknown source of this image. And your task is to find out where this image comes from. So first, it might come from one of these so-called autoregressive models. So these models generate these images by producing token by token. And here, as the first stage, we recommend finding out what is the autoencoder. Autoencoder actually is this part of the models that transfers images between the pixel and the latent spaces. So you might here find out where this image was transformed, which autoencoder actually was responsible for generating a given image. And now within these model families based on the encoder, we have specific model versions. So your task actually is to find out what specific model, which specific generator was responsible for this image. We have also here two families of models. We have models var from var 16, 20, 24, 30, and also RAR models, BL, XL, and XXL. So different model also sizes. So the image that actually we are given in this task 2 might come from one of these versions of the model. However, it might occur that actually the given image is not generated by one of these models, but might be, for example, natural or coming from a different model. So let's say Franziska mentioned that in task 1, you might generate images using infinity to billion, and then this so-called outlier data points, outlier images, that might actually come from a different model like infinity. Now, to summarize, you are given an image with an unknown source, and your task is to label this image using one of these 9 classes. So we have these 9 classes, 4 for different var sizes, then 4 for different rar sizes, and finally the outlier class. How do we really measure your performance on this task? So actually the metric for this task is accuracy, which is standard thing. So what we really do is that we divide number of correct predictions, so how many times you correctly predicted the class, so the source of the image, over the total number of predictions that actually are required for the given task. Now, what are the data sets that actually you will be given and you will have to work with? So these are actually the artifacts for this task. The first one is training data. So actually here we give you labeled in distribution samples. We have overall in total 800 images, and then we have 100 images from each model version. So we have 100 images from VARD16, VARD20, also 100, and so on and so forth. So overall, from all of these 8 different model versions, we have 800 images. We also have validation data that actually contains, apart from these images from the given models, we have 50 images now per a given model version. Also, we have additional outlier images, which are in this case 50 in the validation set. Finally, what is probably the most important is the test data, which is unlabeled. So we have overall here 9,800 images, and the purpose is that you have to label these images. So you have to find out which out of these 9 classes this image is classified. So here, these images actually will be also used to create the score on the leaderboard. And now, if you feel that maybe these are not enough samples for you, you might also use these models. Also, we give the code for the var models and rar models. Also code for infinity from task 1. So you can collaborate. Those who work on task 1 can also help with task 2. And you can generate more images to actually provide more of these in-distribution samples from a given model, or also outliers. Now, a hint. So I talked to some of you, and you mentioned that, hey, I read the papers, and it's very interesting, and I got this really about these tokens and how they are formed. I'm like, great, this is amazing preparation. And we thought that we can also give you maybe some head start so that you can really have fun working on the task. So some of you read the paper actually from our group about finding out the source of the given image. So what we are showing here is natural image of a dog, and we encode the image, so we go from the pixel space to the latent space. Actually, from these latent representations, we form these discrete tokens. So these are these tokens T1, T2, to up to Tn for this natural image. Now, what is the core of these modern models for image generation is the codebook. So actually, codebook contains kind of you can think about the basic building blocks out of which you can generate images. And now this codebook is also used to generate these new images. So also image of a dog, but slightly different. And then if you compare the representations of these images, so how they differ from the representations from the codebook, it occurs that representations from these images that are generated actually are closer to the codebook representations than those that are from the natural images. So you can just think during the task development, how you, when you solve the task, to really think about how to maybe leverage this information about the codebook to find out which specific model the image comes from. Okay, any questions regarding task 2 about model tracer? Okay, here's a question.
So how do we interface our classifier model to the challenge interface, or do we like upload the source ourselves, or does it run on your system?
Very good. So here actually how it works is that we give you this this test data, right? And then your task is to, for the given image ID, to provide the class. So where this image comes from. So basically, your task is for a given image ID to assign one of the 9 classes. So it's on your end how you want to do that. You can do some classification. You can train a classifier model to solve the task. You might delve deeper into these internals of the models to match basically the correct class to the given image.
How do you translate that to the
CSV file.
Ah, yes. So.
How do you put the accuracy in the leaderboard?
Yes. Okay. So this is standard across all the tasks. So we have this API that you will basically interact with. So then you submit this CSV file, which has these images, image IDs and the classes that you got predicted, and we take this CSV file to just, in this case for task 2, to just compute the final score. Thanks for the questions. Okay, great. Anyone else has other questions? Yeah, go ahead.
Do we get the code book?
So basically, we also give you access to these models. So basically, then you can find out like what is the code book, also different internals of these models are open. So it's open source model. You can download the model. We have the code for that. You can just analyze what is inside the model. So to give you intuition. So actually, there are different code books for these different models. For example, like in a VAR model, we have code book with 4,096 entries. There's a bit different code book in RAR. So you might also just find out more about these models, and we give the code for that. So you have also this information, the specific for the given model. Okay, perfect. Any more questions? Okay, if not, we can actually then move on to task 3. So here, for task 3, we have another faculty member from CISPA, Thorsten, and then he's an expert in this.
I'm prepared. Thank you, Adam. And also a warm welcome from my side. As Adam said, I'm also a faculty member at CISPA. My research is more on the security side of ML, but I'm also very interested on seeing how, if we look at a machine learning model, on how an adversary can like force the model in doing things it's not supposed to do. And
so we can just move on to, I move on to your task. So, okay.
So to tell you a little bit more of this, I want to introduce our challenge, which I prepared together with Jonathan, who is one of my PhD students. And in this challenge, we want to look underneath the machine learning model when it's executed in the real world. And in other words, we want to tackle an implicit assumption in the literature on the ML robustness that we usually assume like an ideal prediction function. But of course, if we want to actually execute a machine learning model, it has to run on some computer, on some hardware. And in order to do this, we often implement our ML models with some frameworks such as TensorFlow and PyTorch, which abstracts away a lot of the complexities that would be necessary to actually run the model. For example, back in the days, you would have like implemented your own C code to do like a convolution or so. And nowadays, luckily, we don't have to do anything of this anymore. However, these ML frameworks, they still like needs to run somewhere, and they use like different other components on your computer to be as efficient as possible. And one like major factor in the computation of a machine learning model is like doing like these large matrix multiplications if you want to evaluate a neural network or so. And for this, usually the ML frameworks are built against some mask library. And these are optimized to be as fast, as efficient as possible to do a matrix multiplication depending on a particular hardware. So for example, if you run something on a GPU, you use a different algorithm for a matrix multiplication compared if you run something on a CPU. And of course, depending on which compiler extensions your CPU has, there are different tricks that you can do. And what we are interested in this challenge is that we want to consider a setting where we have like two different learning platforms that execute our ML model, and we keep everything the same except like the use of the mask library. So in particular, this is the same hardware, it's the same machine learning model, it's the same ML framework, and what we are considered is just in the difference of how we do implement the matrix multiplication. And the properties of these libraries is that they all implement the same interface. So mathematically speaking, regardless of which implementation you use on paper, it's the exact same computation. However, if we actually look on what is executed on the platform, we observe that the decision boundaries of our ML models slightly differ. So for example, let's consider that this is the decision boundary of platform A, and this would be the decision boundary of platform B. And what's interesting is that they are very similar, but they are not exactly the same. And in particular, there are these tiny pockets. And these pockets have the property that the classification in these pockets differ depending on where you execute your machine learning model. And before I introduce you what you actually have to do, let's first I want to give some background what is actually going on here, because I find this quite unintuitive when I first saw this. And for this, we need to make a little detour into the floating point representation, which I hope you heard the last time in your computer architecture lecture. And there's one insight that is very important here, is that the floating point numbers are only an approximation of the real numbers. And this is quite intuitive because your floating points have a fixed precision, and of course there can only be an approximate way of an infinite set. So if we take a look at like a 32-bit floating point number, you might recall that like a common way to represent this, that you have 1 bit reserved for the sign, a couple of bits reserved for the exponent, and the rest is used for the so-called mantissa. And this bit string happens to represent the number 0.5. And now the question is, if we consider the next available number in this set, so we would increase the mantissa by 1 bit, then we see that it's still like very close to 0.5, but there's like, it's a little bit higher. And what's important here is that there is a gap between these. So this is exactly like the consequences from the fixed precision. And what this means is that depending on the order in which you do your calculation, you introduce different rounding errors. Or more formally speaking, floating point arithmetic is generally non-associative. And this usually doesn't matter, but if you now think about like very large matrix multiplications, where you have a lot of floating point calculations, then it can happen that like depending on how you implement your matrix multiplication, you can obtain slightly different results. And this is exactly what we want to focus on in this challenge. And we want to study so-called chimera examples. And the basic idea is that you want to have an input that is classified differently depending on the hardware it is executed, given like the same model. And for the task, you will get a set of 1,000 images, and your goal is to find like a perturbation for each of these images to fulfill this task, to move these inputs into the gap between the decision boundaries. And the scoring is then done as a sum over all of the test images, so the 1,000 images. And what we're most interested is in like the effectiveness of the attack. And this is not a trivial thing, so be prepared that this will take a while until you find your first successful image. So this is like the more images you can find, the better. And for each successful images, we are then interested in finding like the ones that are most closely to the original image. So in other words, your score is higher the more images you find, the more similar they are for the original images. Any questions to this? Okay, then I guess.
Really, no questions? I don't believe you guys. Come on. I think task is not trivial, right? Not trivial. There's a question. Thank you so much.
Thank you. Yeah, I had a very general question, not very specific to this task, but
very good.
yeah, it went very quick, so I couldn't really have what they think about questions, but general questions which are, since we have 3 tasks, are we supposed like to start with each task sequentially and then submit them each after one after the other? And if you would like rank the difficulty of each task, so like you give an advice of which one should we start with, which one do you think, how do you rank the 3 tasks difficulty?
Okay, I think it's a great question. I think general question regarding how to approach these tasks. So I would say that, as Torsten was saying, I think that the learning curve is pretty steep for Chimera, right? So probably it will take you the most time to get the first solution, I suppose. Then for the reconstruction, it's also quite some time to get the first image reconstructed. I suppose you can maybe start even from task 2, model tracer, to maybe, as was mentioned by one of the participants. What's your name, by the way? Ahmed. So Ahmed mentioned that, how about classifier? This is also like one way how to approach it. We even actually give for the model tracer classifier to just start with, like Resident 18. It's like, very, very naive solution, but, it's something that you can start with. And then I think that regarding like strategy, so I would recommend that within a team, you can find people who really care about specific aspects. So let's say I talked to one of the teams and they were like, I really love this aspect of like finding out which model or which source really a given image comes from. So if somebody really is passionate about this topic, you should work on this one, right? And then, maybe find within the team who is really interested in which aspect. So you can then work on something that really interests you, right? And then you can learn more about these things. So maybe start from task 2 if you want, and then go to task 1 and 3. But I think that there is no like one, specific rule how to win the hackathon. It's more like you have to just also find out what for you is of bigger interest. Ultimately, the teams that win this kind of regional rounds of the European Championship, usually they have a nice division of who works on what. They also collaborate. For example, like you can have some images from task 1 and also use them for task 2. So there's also this aspect of collaboration here, which is I think very important. So then you have to just find out within the team like how you want to really do that. Does it answer your question, by the way?
Yeah.
Okay, perfect.
Hi. I just want to clarify, this is Chimera, so it's kind of a yes or no. So looking at one of the pictures, we then can say if the boundaries are not equal, or could you just clarify that as Chimera part, how to evaluate if that's a yes or no for a given picture?
I'm not sure if I completely get what you mean. So what we are looking for is an image that, depending on which platform you execute, gets a different prediction. And in order to do this, it needs to be in between the decision boundaries. Because then you are on the left side from the one boundary and on the right side on the other boundary.
So the classification of the pictures are, what are the classes to
make it a little bit simpler for you, it doesn't matter which class it is. So it doesn't have to be the original class.
Yes, the images, could you speak a little bit about them? Are they random images or are they related to the model somehow?
So you will get access to a tiny VGG style model, which is trained on a CIFAR dataset, which is like also quite small images, 32 times 32. And you will get access from 1,000 images sampled randomly from the test set. So the model has never seen these, and your goal is then to manipulate each of these samples.
Okay, and the submission, is it just as many images as possible that are chimeras?
So the best case is that you, for each image, you have like the corresponding chimera, which looks very similar to the original image. And but you will find out, so you will start with a couple, and then as soon as you have like something that slightly works, it's usually like easier to extend this, that you also find more chimeras. And what we are in the end are interested in just the images. So as soon as you find one, you can keep it in theory until the end, or that you will find a better one.
Can I ask another? Yes. So yes or no question for is it a chimera, but what does minimize perturbation mean?
So in order to create this chimera, you need to move the image onto the decision boundary. And depending on where the decision boundary is located in the model space, you can find like an image that is closer to the original one. So you need to perturb the original image to move it, and depending on how big these perturbations are.
Thank you. Okay, thank you for these questions. Any more questions? Maybe also about any task.
There's one more question. Some exercise for Nima. The next question in the front, please, again.
On task 2, it's we get the labeled images and we get the test images, which I assume you're scoring on. Maybe I don't know, maybe this is too much of a clue to ask, but what is the purpose of the labeled images?
Okay, so actually this is for you to get started. So this is something that gives you the initial training set, for example, for classifier you can start with. So this is initial starting point that enables you to start fast. You don't have to go to VAR or RAR models to generate images. You can just take our pre-generated images and start with them. And also what is I think important is, for example, validation set has also these outliers. So you also can get understanding of what are other images that we are using as outliers in the task, which were not generated from VAR or a RAR style model. Okay, thank you. Thank you, Evie, for the question. Any more questions? Okay, I think that. Thank you so much for these very important questions. So we can just move on to one more aspect, which is about compute. So I think that, as you saw, some of these tasks require a lot of compute. So also, we don't leave you alone on your own to just find the compute to work on your laptop. No, we also provide actually very beefy servers. So thanks to Jülich, which is a computer center in Germany, we are grateful that they enabled us to use their infrastructure and many servers for you guys to work on them, so that you have enough GPUs, enough CPUs to develop solutions to these tasks. So we have overall more than I think 40 compute nodes for this hackathon. So if you haven't done that yet, please go and register. I think most of you actually did that. Please also register with your email address from the best case university or your company, because then actually I know that, okay, it's not like a fake person, but this is a real person. So the best is if it matches the registration, just to make sure that we don't allow anybody else to get into these resources and you can really use them fully. So also we have to accept this terms of usage. Also there is something like authentication, two-factor authentication. Use your favorite tool. I use Google Authenticator, but whatever you use, you can just always take that and use for Jülich. Sign this usage agreement is just to make sure that you work on the tasks and not to, for example, compute something for Bitcoin. So this is an important aspect. Most of you, I think, are already able to access the servers and then SSH into that. So if you haven't done that yet, you have to create your SSH key. Very easy. You have also even here the command SSH key again. This is your way to go to generate your SSH key. If you have already one, just reuse that also for access to these servers at Jülich. Now, once you do that, actually you have to also specify IP addresses from which you actually access these servers. So just copy paste. They give you IP addresses from where you are. Just copy them, and then it should work out of the box. And then what's important is that once you request access to this project training 2601, I have to accept it, so it should be very fast, especially now. And after like sometime, a few minutes, maybe up to 15 minutes, service has to be updated, but you will eventually get access to the Ulyss servers. Then once this is done, you will be able to just use SSH and your login at Jureka fz ulyss.de, and you are then on the Ulyss servers. So how we usually develop the solutions to these tasks? Usually we use VS Studio Code. I think most of you, also from the previous versions of these hackathons, actually we also know that most of you use this tool. So this is just a small tutorial regarding how to develop the tasks, develop the solutions to the tasks. So click in this bottom left corner, and then you can basically connect within the VS Studio Code to the server on Ulyss. This is just a SSH connection, standard thing. Then you have to choose the host, so you just can configure SSH host. It's very easy to do that, actually. Just choose one of the config files, and then over there just put this, just copy these lines and put in these config files. Especially for the Windows users, so for Windows you have to add this last line with the max, just to be able to easily access the servers. So once you do that, you have this Ulyss server. You can just click on that and you connect to the Ulyss infrastructure. Then you can, through the VS Code, you can choose a terminal. You have a new terminal over there. We always recommend that you use this command jutil and activate -p training, in this case 2601. This is just our allocation on these Ulyss servers for you to work on these tasks. And then what we recommend is that you also git clone the repository. Is it working, Maitri? This one? We can also set this up probably just for you to get easier time to get started with the tasks. Okay. There is also in every single task we have also sample submission. So this is something that you can at the beginning use to submit a first solution. Can be even random, just to check if the API works for you. So there is this file for you to just get started. But this gives you just random solution. So it's just check if the API from us really works for you. We'll also send to you very soon these API keys, right? Mm-hmm. And then this actually API key has to be used by every single team. So each team has its own API key. This actually is identifier for your team, and then we match it with your team name, and we will have these team names in the scoreboard that you can see where you stand. So how you compare to other teams. So. Yeah.
And maybe one important thing is that this API key is basically your key for every single task, but the cooldown times from the task do not interfere the others. So let's say you're one person working on task 1, you just submit it for task 1, so now you need to wait 5 minutes, but the person from task 2 can submit at any time, and like their 5 minutes will start once they have submitted there. So they are like the same key over all tasks, but independent cooldowns.
And then what we recommend for managing the packages is UV. So actually this works very fast, and from our experience from the past hackathons, really the easiest way to go is just using UV. It's very easy to get started. You just use this curl command, and then you just install UV. In this case on Ulyss, it's blazingly fast. Now once you do that, also we recommend putting these literally 3 lines of exports in your bash.bash rc file. It just enables you to just use UV much easier. And also the other tools. There are 2 versions how to do that, but basically you can just literally copy these commands to your .bash rc file and you are done. Now what is important is that you also have this specific macros like $project, so you can just go over there. This is basically more space for you to keep the models and data, so use this also specific $project as the place where you basically develop your tasks.
And maybe one important thing there is to also make sure that you generate your folders such that only you can see them. Like in the past, there have been things where people have generated their folders such that everybody could see them. And of course, because you're still competing with other teams, I would just recommend make sure who has access to your files.
So Maitri has such basically list of commands and a document where you can also read through how to get this done. But basically, once you have this UV, you can just the UV init, p, and also Python version in this case. So for each task, you can have separate environment, and then every single task is a bit different, so you can have separate environments per task. Now, this is a submission script. So once you develop initial version of your solution, you create this bash script. This actually is the standard script to start a job on the cluster. So then you can copy basically that, and then run this. So srun, you just run this Python sample submission.py, and basically this actually enables you to use the main resources with, for example, many GPUs. So this is really the batch job that you should use to get most out of the hardware at Julius. Now, once you develop this script, you just do sbatch and this script name, in this case main.sh, and actually this is the command to submit the job to the Julius cluster. Now, you can also see this GPU. So once you are on this specific server from Julius, you can use at a given point in time 400 GPUs, each with 100 gigabytes. So you have a lot of resources at your disposal. Any questions regarding infrastructure? Over there.
We use our own.
Sorry, I didn't get it.
Is it okay if we use our own infrastructure instead?
Yes, of course. I mean that if you want to use your own big servers, by all means. I mean that this is from us for you to, you know, even if you are a student at university anywhere, you don't have big hardware at your disposal, no problem, we give it. But if you have enough resources on your own, even better. Then somebody else can use these resources, right? So perfect. Also, if you are already familiar with other cluster, it's maybe easier for you. We don't mind. Ultimately, what we care about is the scoreboard and your solutions and your presentations. So basically, we enable everyone. If you want to work on your laptops, no problem. This is only to enable you to work more efficiently. Perfect. Any more questions? Okay, so we can just say a few more things. So here, actually, Julian provided us with the mapping, the room number in the first column and the team number in the second column. So we have 4 rooms where you can work on the tasks, and then we have basically setup of the tables so that you can sit together as a team at these tables and work on the tasks. So you can also take photo of that, and you can also find which room you will be working in.
And also the email that I'll be sending out, like once we have now found a team for the last people who are still looking at team, then I'll do this job like of sending out all the emails to all of you, and it will also again have all your information, like your name, your team number, and your API token. And so you will have everything in one place.
Probably one more thing is that, you know, have fun. And we are here for you, really. So if you have any questions, just grab us, you know, and then ask us these questions. And we are here to really help you to learn, to enjoy, and hopefully by tomorrow at 12:30 we have amazing solutions. I'm looking forward to talking also to you guys and getting to know you. So hopefully you will enjoy it. You will have amazing Valentine's Day with us. And
have fun.
Have fun. Thanks.